Welcome! I am Karen McFarland, the punk rock professor, and I am here to give you clear and concise tools to help you crush chemistry. It is so great to have you here. We're going to be talking about molecular orbital theory, and specifically I wanted to talk about calculating bond order and also how bond order changes if you get an excited state in the molecule that you're looking at. So if a photon comes in, excites an electron, how do you figure out what the bond order is then? So we'll look at some different scenarios and talk through some of the concepts that are important with looking at bond order in molecules. Okay, so first off, we need to create the molecular orbital diagram. And where we're going to start out is with the simplest molecule that exists, and that is hydrogen, H2, the H2 molecule. All right, so the H2 molecule, we have two hydrogen atoms coming together, bonding, forming this molecule. And that is exactly, when I do that, that's exactly what our molecular orbital diagram is going to look like. We will always have the atomic orbital energies for the atoms themselves on the outside, flanking what the energies are of the molecular orbitals in the center. All right, so let's take a look at what this looks like. A molecular orbital diagram, we want to think of it as an energy diagram. So we always think of energy being off here to the side, and it is increasing as we go up. All right, so that means lower energy, more stable. Higher energy, less stable. Okay, so we'll keep that in the back of our minds. And then we will also, as I said, we will think about these two atoms that are separate to start with, but when they come together and they form that bond, we have then the H2 molecule. And this is really going to be our focus. But it is helpful to think about what are the energies of those atomic orbitals before they combine together to form the molecular orbitals. Okay, so in terms of those atomic orbitals we're looking at for hydrogen, this is the 1s orbital for both of those, equal in energy. Okay, our s orbitals, these nice spheres, all right? So we've got those orbitals there. We'll put electrons in when we're all done. But here we want to consider what happens when those two 1s orbitals get close to one another. Okay, they come close to one another, and we have two things that happen. From the standpoint of molecular orbital theory, we consider electrons as being waves, and so that means that there can be constructive interference of a wave when the amplitudes add together and you get a larger amplitude. That corresponds to there being a greater probability of finding an electron when we have that additive, that constructive interference of the wave, of the electron wave. Okay, alternately, we have this possibility where we have destructive interference. So if we think of electrons as waves and destructive interference is going on, then that means we will then have a zero amplitude and zero probability of finding an electron. Okay, so this whole wave-like nature of electrons is not intuitive, but it is something we need to keep in mind when we're thinking about molecular orbital theory, because this is quite relevant when we then look at the molecular orbitals that are being created. So we have the creation of these new molecular orbitals from atomic orbitals when they come together, and there is constructive interference and destructive interference. Okay, so we are essentially looking at what's known as a linear combination, but what that means is that we consider what happens when we add the two orbitals together and when we subtract the two orbitals from each other, when there's destructive interference where they're overlapping. All right, so if we've got these spheres here, if we think of this as our nucleus of the hydrogen, and we have this 1s orbital around it, and that's also what our 1s orbital over here looks like. Okay, and now we imagine them coming together, overlapping. All right, and so they would then, let's draw what happens when they overlap here together. Okay, there's our nuclei there, and they're overlapping. And what happens when there is constructive interference? When you're adding together that probability of finding an electron between the two nuclei. We're going to have an even greater probability of finding an electron between the two nuclei in here. Okay, so that's fantastic for the stability of the electrons. If you can put an electron between two positive charges, we have a nice Coulombic interaction there, meaning positive, negative attract each other. An electron can sit there nestled between the two positive charges. Lovely, okay? And that promotes stability, overall stability. So this particular molecular orbital that's been created is nice and stable. And remember what we said about the energy? More stable, lower energy. Okay, so we have a molecular orbital that has been created by the overlap and constructive interference of those electrons, okay? Lower in energy. Now, what do we call this? It's always nice to have labels so we can keep track of things. What do we call this molecular orbital? All right, well, the name of this molecular orbital comes from the fact that we are really considering what's happening between these, directly between the two nuclei. Okay, that is a sigma interaction, we call it, when we've got electron density between the two nuclei, directly between them. And that is where this molecular orbital gets its name. So this is known as a sigma molecular orbital, and it is bonding. Okay, so I'm just writing bonding here. When we usually draw out an MO diagram, we don't have to say exactly bonding. That word doesn't have to be written there. I'm just writing it for us to keep track of what's going on. Okay, and then there's the alternative. There's the destructive interference that can happen. So what that means, and I'm going to draw this up here. I want to make sure I have enough room here. I'll put it here. So let's consider once again, if we have this one s electron, this one s orbital, and this one, and they're overlapping, but now destructive interference is happening. We're going to subtract the overlap. Okay, so essentially what we have done is we have put in a node. That is a place where there is no amplitude, there is no probability of finding an electron. And very often we show nodes by drawing a dashed line. No electrons are there. So I'm even going to delete that and maybe just redraw that, that we've essentially subtracted out. What's the electron density between those two nuclei? This molecular orbital we now call an anti-bonding. It is destabilized. Now it still has that name sigma because we're still considering what's going on directly between the two nuclei, but we call it anti-bonding, and the symbol for that is an asterisk, okay, our sigma star molecular orbital. So I'll write this here, anti-bonding. All right. So now let's put in those electrons, and this is where we can think about each one of those atoms. How many electrons do they have? Hydrogen, just a hydrogen atom. It's got one electron. That hydrogen, one electron, okay? So now we take all the electrons from each of the contributing atoms and we dump them into the molecule. So we've got 1 and 1. We're going to put in 2. Now, we've got to have them have opposite spins, so spin up and spin down. All right, that's okay. We're just taking those electrons or putting them together. So don't worry about flipping the spin here or anything like that. We're just going to put in those electrons. All right, so we have constructed our molecular orbital diagram, and we can look at the bond order. This is going to give us an overall viewpoint of how stable is this molecule, how stable is that bond that is between the two hydrogens. And so our calculation for bond order, we'll put it over here. BO, I love that abbreviation. Bond order. This is taking all the electrons that are in bonding molecular orbitals, so bonding MOs, and because those are stabilizing forces, those are electrons that are stable, and we're going to subtract out anything that's destabilizing. So that would be any electrons in the anti-bonding orbitals. Okay, so there's our bonding molecular orbitals. Subtract out the anti-bonding molecular orbitals. And we're going to take that, whatever value we get there, we're going to divide it by 2. Okay, the reason for that is that we're looking at, for example here, a pair of electrons, but a bond, a single bond, is 2 electrons. So if we're adding up all the electrons, we're going to divide that by 2 to give the overall bond or bond order. That gives us an idea of the strength of the bond. Okay, so in the case of H2, here's our 2 electrons, those are bonding. Okay, so bond order of H2, we would then say, all right, we've got 2 electrons are in the bonding molecular orbital, 0 are in the anti-bonding, and we divide all of that by 2, and that gives us a bond order of 1. All right, lovely, because that is consistent with what we would predict if we were to just draw a Lewis structure. Okay, a Lewis structure of hydrogen, Lewis dot structure, would just be a pair of electrons between them. You could also draw it this way, which shows a single bond. Single bond, bond order of 1, consistent with each other. Okay, so this is ground state hydrogen. Now, what happens if a photon comes in and excites one of those electrons? So let's say we've got photon comes in, hits one of these electrons, and it's going to move. It's going to jump up. All right, photon. Oh, here's our photon. I didn't label it. Photon comes in, hits an electron. Okay, comes up here. All right, we are now in an excited state. Sometimes you put a little star there to show an excited state of a molecule. Doesn't mean anti-bonding, just excited. Okay, we've got an electron up here. And now we could calculate the bond order of this excited H2 molecule. So let's use that same equation if we're looking at the bond order of the excited state. We've got 1 electron in a bonding molecular orbital, 1 electron in an anti-bonding orbital. We divide it by 2. What do we get? 0. Okay, a bond order of 0. What does that mean? That means no bond. There is no overall stabilizing force. We have an electron that is in a stable bonding molecular orbital, and we have 1 electron that is in an unstable, pretty close to equally unstable anti-bonding orbital. They're going to negate each other. And so what is this molecule going to do? If it has a bond order of 0, there is nothing keeping those 2 hydrogens together. They are going to dissociate from each other, and we have broken that bond. Okay, so putting in a photon that causes that electronic transition up to anti-bonding, we're going to break that bond. Okay, so think of bond order as how stable is this molecule. And if you ever have a bond order that is 0 or less, then that molecule is not stable enough to exist. It will break apart. All right, well, I hope this was helpful. And if it was, then please subscribe. It helps me keep these videos coming. And now it's time for the bonus track, and I want to show you my t-shirt here. Really, really cool design. The name of this band, I don't know if you can see it, I hope so, is Typhoon, and they're from the Pacific Northwest. They are an amazing band with super talented, amazingly talented musicians. And I happen to know a couple of them. And in fact, the bass player in Typhoon, I used to play in a band with. And they have this amazing video. It is called Dreams of Cannibalism. Incredibly done. Matthew Ross did it and made the video for them. And they filmed it in Salem, Oregon, where most of them are originally from, at the Enchanted Forest. And fun fact, my son is in the video. He's the star. He's the kid with the hat. And it tells a great story. It's definitely worth checking out. Typhoon is worth checking out. And I just want to thank you for hanging with me till the end. I hope this was helpful, and I will catch you next time.